Hello. So in this video, we are going to go over complex numbers, and in particular, how to identify the patterns of the powers of I, which is the imaginary unit, and how to do operations with complex numbers. So how to add and subtract complex numbers, how to multiply complex numbers, and how to divide complex numbers. So we're going to start out first by talking about the imaginary unit I. So, complex numbers are their own set of numbers with their own set of rules. We have our rules for real numbers, which show us that we can add and subtract numbers, we can multiply, we have distributive property. We've learned all of those properties. So, we're going to talk really quickly about the properties of complex numbers. So, we have the imaginary unit I, and I is equal to the square root of -1. So from that as our first kind of unit there, we can increment the powers of I. So if we take I and we square it, that would mean we have to square the square root of -1. And so when we do so, we find out that I squared is equal to -1. And this is another kind of important unit there, that's foundational to everything else that we're going to do. So it's important because the square root of -1 became a really big problem for us and for mathematicians long time ago, when we're trying to factor and use the quadratic formula. And I'm sure you've seen many times when you try to apply the quadratic formula and you end up with a negative number under the square root. And so you think, okay, there's no way to find a factor for this. So there is, in fact, a factor. However, it's just imaginary. So we'll look into more of the history behind that later, but right now we're going to focus on the patterns and how the properties apply. So we've figured out that I squared is equal to -1, and then what we'll do is we'll take I squared and multiply it by I, because that will give us I cubed. And so that would mean we have to take -1 and multiply it by I. So then we're left with I cubed is equal to -I, which we can see on the chart here. And continuing with this pattern, we take I cubed and we multiply I cubed times I. So that will be the same thing as taking -I and multiplying it by I. And so we figure out that I to the fourth is equal to -I squared. And again, noticing patterns here, we already know that I squared is equal to -1. So if I plug that in here, then I can say that I to the fourth power is actually equal to 1, which we see written out here in the chart. Now, if we continue this process with all the different I powers, notice that as we go through I to the fifth all the way through I to the eighth, there's a pattern emerging. And that pattern is we're repeating the same thing again, right? So after I to the fourth, the pattern starts over. So you see I to the first is the same thing as I to the fifth. I squared is the same thing as I to the sixth, and so forth. So what we can do is we can start to assume that if we were to do I to the ninth power, following this pattern, it's going to equal I. And then later on, I know that I to the 12th power is going to equal 1. So our pattern here is the powers, right? The powers, as long as they're they're divisible by 4, then it's going to equal 1, right? If it's not divisible by 4, we're going to look at the remainder, and the remainder is going to determine what level in the whole rotation we are at. So let's take a look here at the rules to figuring that out. So we've noticed the patterns. Now we are establishing rules that will work every single time that we need it to work for us. So if we have I to whatever power, that power, we're going to call it n. And so what we need to do is analyze what n is and check to see what we get when we divide n by 4. So if we divide n by 4, and if n is less than 0, then we're going to look at the remainder. If n divides by 4 and there's no remainder, then we know our answer is going to equal 1. If n, when we divide it by 4, we're left with a remainder, then we're going to look at the next part, right? If the remainder is positive 1, then it's going to equal 1. If the remainder is negative 1, it's going to equal negative I. So we're going to do some examples just so you can see how this works exactly. So this first example, I to the 53rd power. So 53 is what my n is. So what I want to do is I want to take 53 and divide it by 4. Now 53 divided by 4 is going to be 13, but I'm left with a remainder of 1. So I'm going to look at the chart. I know that my n is greater than 0, so I'm looking over on this side, and my remainder is 1, so I know my solution is going to equal I. I to the 53rd is equal to I. So it's a kind of like a shortcut way, instead of having to multiply I so many times, right, 53 times, we divide it by 4, so that way we can kind of shortcut through all of the steps and find our solution here. All right, so let's try this next one here. We have I to the negative 18. So negative 18 divided by 4, that's going to equal negative 4 with the remainder of negative 2. Because I know that negative 4 times positive 4 is negative 16. And so in order to get from negative 16 to negative 18, we have to go down 2. So that's why our remainder is a negative 2 here. So I'm going to go to the chart. I know that my n is less than 0 because my n in this case is negative 18. So I'm looking at the chart on this side over here, and my remainder is negative 2, so I know that my answer is negative 1, just based off of the chart. I to the negative 18 is equal to negative 1. All right, so maybe you want to try and pause the video for a second and see if you can try I to the 25th on your own. So in this case, our n is equal to 25. And so 25 divided by 4 is going to give me 6 with a remainder of 1. So I know that my n is positive, so I'm over on the right-hand side here where n is positive. And my remainder is, what did we say? 1. So my answer is going to be I. I to the 25th is equal to I. All right, last one here, I to the negative 12. So I'm going to say that my n is negative 12 in this case, so we're on the negative column. And negative 12 divided by positive 4 gives me negative 3. So I have, and my remainder, because 4 goes into negative 12 perfectly, my remainder is 0. So I'm going to come up over here. Let's erase all this so we can have a clean slate here. I'm on the left column because my n was -12, it's negative, and my remainder is 0. So I know that my solution to this problem is equal to 1. I to the -12 is equal to 1. So why would this be helpful to know how to do? The biggest thing is we're simplifying, right? The directions literally say to simplify. So it's a lot more nice to work with the number 1 in this case than it would be to work with the number I to the -12. I think we can all agree on that. So that is why we want to know how to simplify this so that we can have easier numbers to work with. Now we're going to look at how to add and subtract complex numbers. So it works much like we add and subtract real numbers, regular numbers that we're used to. The only difference is you want to make sure and only add and subtract the components that match up with each other. So each complex number has two parts to it. It has the real part and it has the imaginary part. So the real part is the number that normally you see in front. And sometimes if you are seeing something that looks just like this, then the real number is just 0 in that case. But there's always going to be some kind of a real number. Just like if you're given any number, like let's say the number 6, technically there could be an imaginary part there. It's just 0 times I, right? So it's a little bit of notation there. So the real numbers are always going to be added together, and the imaginary numbers are going to be added together. So kind of the same PEMDAS rules apply. We'll just combine like terms. You can think of it that way, right? The like terms in this case being 5 minus 2 because those are the real numbers, and then we'll add -3i plus 4i because those are the imaginary numbers. And that's going to give us 3 plus I, and that is our solution. Simple as that. So if you want to, you can think of it as combining like terms because the terms are alike in that they are either real or imaginary. Be careful with the signs. Here we're subtracting two complex numbers, so we want to distribute that negative. So this is technically going to be 10 minus 2i minus 14 plus 6i. And so when I combine my like terms, 10 minus 14 is -4, and -2i plus 6i is going to give me 4i. And that is our subtraction. I suggest maybe pressing pause and trying this one on your own before we go through it together. So we have 4 minus I plus -3 plus 5i. So I'm going to check, with addition, you don't really need to distribute it because it doesn't really change the sign. But we can always think about how we need to do that. Combining the like terms, we're going to have 4 minus 3, which is 1. And then we're going to have -I plus 5i, which is 4i. So that is our solution here. And let's take a look at the next one. We're subtracting two complex numbers. So we'll distribute that negative. We get 8 minus 5i minus 4 plus 2i, because negative times negative is positive. And we get 4 minus 3i as our solution. So that is adding and subtracting complex numbers. Let's move on to multiplying. So when you're multiplying complex numbers, the same distributive property that we use when it comes to multiplying binomials will apply. So for example, if you had x plus 2 times x plus 3, you would multiply this by multiplying your x's, and then multiplying x times 3, and then multiplying 2x, and then multiplying 2 times 3, and adding that all up. So the same process applies here. We have 2 minus 3i times 7 minus 4i. So I'm going to go ahead and distribute that. 2 times 7 is 14. 2 times negative 4i is negative 8i. And then we'll distribute these two. Negative 3i times 7 is negative 21i, and negative 3 times negative 4 is positive 12. And remember, these i's have to be multiplied as well. So I times I gives me I squared. Okay, so from here, once you've distributed, we combine like terms. So we've got, right now what I can see is those two terms that have I in it, I can subtract them. So I get minus 29i. And while we're at it, we have this I squared. So this is when it's useful to know what I squared is equal to. I squared is equal to negative 1. So I'm going to go ahead and replace the I squared with negative 1. And so we see how it helps simplify our problem and puts it into a more standard form for us. So we've got 14 minus 29i minus 12, and then we combine the like terms of 14 minus 12 because those are the real numbers. We get 2 minus 29i. And this is in our standard form because we have the real number and then we have the imaginary number as well. So that's one whole complex number. So let's do the next one together. 4 plus 5i times 4 minus 5i. So we will start by distributing. 4 times 4 is 16. 4 times negative 5i is negative 20i. And then we've got 5i times 4 is positive 20i. And 5i times negative 5i is going to be negative 25i squared. Remember, these i's again multiply to give you a square. So minus 20i plus 20i, when we combine them, that gives us 0. And we're left with 16 minus 25. And this I squared, I'm going to go ahead and plug in negative 1. So now we have 16 plus 25, and that's going to equal 41. And so we see here that this time around, when we multiplied the two complex numbers, it simplified to just a real number. So we're going to look at a little more in detail why that happened or how that happens in just a few minutes. But keep that in mind there. And maybe pause the video and try this one on your own. And we're going to go ahead and distribute. So 2 times 6 is 12. 2 times 7i is 14i. Negative 3i times 6 is negative 18i. And we've got negative 21i squared. We want to combine the like terms. So in this case, we've got 14i and negative 18i. And that's going to give us negative 4i. And this I squared, I will change that to negative 1. So that becomes plus 21. And positive 21 plus 12 gives us 33 minus 4i as our solution, which turns out to be a complex number. And last but not least, 3 minus 2i all squared. So what that means is we are going to multiply 3 minus 2i by itself and go ahead and distribute like we do. We get 9 minus 6i minus 6i plus 4i squared. Combine our like terms, 9 minus 12i. This I squared is -1, so we've got 4 times -1. And that'll become 5 minus 12i. And that is how we do our multiplication of complex numbers. So, before we do division of complex numbers, we have to think about or learn about what a complex conjugate is, because this is going to be our trick to being able to divide complex numbers, because we can't technically divide a complex number by a complex number, not manually at least. We have to do some work before we can do that. So we have to do work in order to turn it into a complex number divided by a real number. So if we think about it, what example have we seen so far that takes two complex numbers and turns it into one real number? Well, we saw it in our example here. 4 plus 5i times 4 minus 5i gave us 41, which is a real number. So what is it about this specific problem that made it so that we ended up with a real number? There's something about it that's a little bit different from the other problems. And if you look closely, this problem here, you may think should have also been a real number, but what I want you to pay close attention to is that sign in the middle, because what we see is a pattern. We see that both the real and the complex parts, the imaginary parts, have to be the same, which we can see is true for this bottom problem as well, 3 minus 2i times 3 minus 2i. But the difference is these are both minus, and this one is plus or minus. And that is what we call a complex conjugate. It's when we have a real number that is the same and the imaginary part that is the same, and the only difference is the sign in the middle. They should be opposite. One should be positive, one should be negative. It almost makes you think of the difference of two squares. Remember the difference of two squares, if you have a squared minus b squared, then that gives you a plus b times a minus b. Those are called conjugates of each other. These, in this example here, they're not complex because they're not complex numbers, but they are conjugates. And they're conjugates because of that difference in the sign. So complex conjugates, when we multiply them, gives us a real number. And we can see that being kind of played out here in this proof. If we were to distribute this, and a and b just kind of represent any number, we end up getting a squared minus abi plus abi minus b squared times I squared. And those two cancel out. We're left with a squared minus b squared times I squared, which we know is -1. So it simplifies to a squared plus b squared. So this is a nice little shortcut that we've just proven. And it tells us that anytime you multiply complex conjugates, all you need to do is look at the a and the b of the complex conjugates and take the sum of its squares. And then together, that's going to give you a real number. Now, let's look at an example for division. We have 5 minus 3i. Oops, sorry. Lost my place here. Really lost my place here. Oh, now I passed it. There we go. 5 minus 3i divided by 1 minus 2i. So I'll write it out as a fraction like this. We can't divide a complex number by a complex number, just like straight down. Is not possible. So what we need to do is turn the denominator into a real number. So what did we say turns complex numbers into real numbers? When we multiply them by their complex conjugate. Now the tricky part here is this is a fraction, so whatever we do to the bottom, we also need to do to the top. So I'm going to need to distribute in order to multiply across now. So this is going to give me on the top 5 and plus 10i minus 3i minus 6i squared. And at the bottom, since these are complex conjugates, I know we've proven it up here, my solution is going to be a squared plus b squared. And how do you determine a and b? You just look at your complex conjugate and you see the number in the front, that's your a, and then you see the number multiplying your I, that's your B. So that's how we got 1 squared plus 2 squared. From here, we're going to simplify. So simplify the numerator. That's going to give us 5 plus 7i minus 6 times negative 1 divided by 1 plus 4 is 5. So see how we just turned that denominator into a real number? That's what we needed in order to actually divide. And then we're going to keep simplifying the top part. I see here we've got 5 plus 7i plus 6 divided by 5. And so that's going to simplify to 11 plus 7i divided by 5. So this is technically simplified already. We've got only one complex number and it's being divided by a real number. So we can stop there, or we can kind of break it down and turn this into 11/5 plus 7/5 I. So this turns it into a more standard complex number because you can see very clearly that we have the real part of the complex number and we have the imaginary part of the complex number. So that will be our final answer. If you want to try pausing and maybe do this problem on your own, we'll also go over it together now. We've got 12 plus 3i, and it's being divided by 1 plus 2i. So again, can't divide two complex numbers unless we turn the bottom into a real number. How do we turn it into a real number? Multiply by the complex conjugate. How do you find the complex conjugate? You pretty much rewrite the same thing, but just change the sign. So over here, we originally had a minus, and so the conjugate was a plus. Over here, we originally have a plus, so the conjugate is a minus. And whatever we do to the bottom, we have to also do to the top. So we're going to multiply these two together up top, FOIL it out, and that's going to give us 12 minus 24i plus 3i minus 6i squared, divided by our denominator, which is the multiplication of the conjugates. So all I would need to do again is take the a plus the b, oops, not literally writing b, our b is 2, and we square each of those and add them together. So we've got 12 minus 24i plus 3i. Those will combine to give us minus 21i. And then minus 6 times negative 1, because the I squared is equal to negative 1. The bottom, we've got 5 again, because 1 plus 4 is 5. And then let's finish simplifying. This is 12 minus 21i plus 6 divided by 5. And that will become 18 minus 21i divided by 5. And again, this is totally a complete answer, but if we want to put it in standard form of a complex number, we do want to split it apart so that way we can see very clearly, again, the real part, which is 18 over 5, and the imaginary part, because every complex number has both of those pieces. And now we've gone through all the patterns and operations of complex numbers. Take care and have fun doing some more practice problems.